Hey everybody, welcome to our week 4 lecture and intro to analysis. Last week we finished off talking about integration, and this week we're going to talk all about integrability. We're going to introduce the Darboux integral, sometimes known as the Riemann integral. We're going to talk about integrability criteria, and we're going to look at integrating continuous functions and prove a few theorems about integration. Okay, so recall the definition of a definite integral that you may have taught your students in Calc 1. So the whole idea with integration is we're trying to find the area under a curve between two endpoints. So if you have A and B, and I'm trying to figure out the area under this curve, I look at the integral from A to B of f of x, and I can compute this directly. Now, you're probably introduced to this limit definition when you first learned about integrals, and the idea behind this definition is that we are partitioning whatever interval you're given into rectangles. Okay, so we could have a rectangle here, rectangle here, rectangle here, and this is not the best sketch, but the point is that the more rectangles you can add in this interval from A to B, the better your approximation of the area under the curve is. Right now, the approximation's not great because when I add up all of the areas of these rectangles, you're going to get a bunch of area up here that's not relevant to the area under the curve. So the idea here is we're going to let the number of rectangles go to infinity, and delta x is going to be the width of these rectangles, and f of xi is going to be the height of each rectangle. And xi depends on if you're choosing to evaluate at the right endpoint or the left endpoint or perhaps the midpoint. But the point is that you're just adding up a bunch of rectangle areas, height of the rectangle times width of the rectangle. And when we let n go to infinity, these rectangles get super, super skinny, and the area approximation gets better and better. Okay, and so here I have some of the things that I just said here. Delta x is going to be the width of the rectangle, so that's the difference, sorry about that. That's going to be the difference between B and A, and depending on how many rectangles you want, that's what you're going to divide by. So that's going to be the width of each rectangle. And xi, for our example, we'll take xi to be the right endpoint. So what you're going to do is, x0, for instance, is the starting point of this, partition of A to B. And when I equals 0, we get x0 equals A. Okay. When I equals 1, we get x1 equals A plus 1 times delta x. Okay, and then x2, we're adding on 2 times delta x. So, you can see in the picture, if this is x naught and we're adding on delta x to A, we get that the next endpoint is right here, x1. So we're looking at the rightmost endpoints here. And that's where we're evaluating our function to get our height. Okay, so just as an example, let's go ahead and recall that we can approximate the area under the curve f of x equals x squared from 1 to 3. We can use as many rectangles as we want. Again, the more rectangles you use, the better approximation. But let's just look at this with 3 rectangles. Okay, so what do we have? Our formula, our formula says that we're going from I equals 1 to n. Now, I'm going to use 3 rectangles to approximate this area. And we're going to do f of xi, and f is x squared. So f of xi is xi squared times delta x. Now delta x is the difference in the interval, so 3 minus 1, divided by how many rectangles we have. We're using 3 rectangles to approximate, so this is going to be 3 minus 1 over 3. And as I just mentioned, this xi is going to be a plus I times delta x. So this becomes 3, I equals 1, a plus I times delta x squared times 2 over 3. And delta x, again, we can go ahead and replace some things in here. We know that a is going to be our starting point, which is 1. So I can just replace this with 1 plus I, and we know that delta x is 2 over 3. So it's going to be the width of each of these rectangles is 2 over 3. Okay. Okay, and we can expand this out. This is just a finite sum. So this becomes 1 plus I equals 1. Well, 1 times 2 over 3 squared times 2 over 3 plus I equals 2. 1 plus 2 times 2 over 3 squared times 2 over 3, and finally 3. So I equals 3. We have 1 plus 3 times 2 over 3 squared times 2 over 3. And if you do the computation here, I'm getting 11.5, where the actual value, so the actual value is approximately 8.7. So the actual area under the curve is 8.7. Using 3 rectangles, we do get an overestimate because of this area at the top. Okay, so again, we're just looking at these, the rectangle areas where each of these bases is 2 over 3, and the height is going to be f of xi. Okay, so f of x1, f of x2, and so forth and so forth. So that's just a little Calc 1 review here. So let's talk about generalizing this idea to integrate more interesting functions using that limit definition. So the idea is that we want a more generalized approach. Now, if you continue in your analysis journey, it's going to get even more general than this. But the idea here is that with functions that are either continuously increasing or decreasing, it's easy to determine what the highest and lowest point on an interval is, right? If it's monotone increasing, such as this function right here, the highest point on the interval is going to be the point at the very end of the interval, right? So this guy's the highest point on this interval, this guy's the highest point on this interval, and so forth. But that's not always the case. We don't always have monotone increasing functions. Consider a function like this, okay, where it's going up and down and up again. We can make the rightmost point the highest point. That's fine on the intervals, but notice now that we don't have the same uniform length of each interval like we did in the monotone increasing case. Now the lengths of these, or I should say the widths of these rectangles vary. Right, this rectangle has a bigger width than this first one, and this one has kind of a width in between the first and the second one. So yes, we can make the rightmost point the highest, but the cost of doing that is that the rectangle widths are not uniform. So we need a few more tools to handle this, to be able to generalize our theory of integration to more interesting functions. Okay, so let's start with a definition. Okay, and I've used this word, but we haven't defined it yet. So let's talk about it. So this is how you find the width of your rectangles, and we start with a partition. Okay, so if we have an interval from A to B, a partition is going to be a finite set, x naught through xn, so that your starting point of your interval is equal to x naught, and your ending point of your interval is xn, and the order is what you would think it would be. We can order this set of numbers in our partition so that x naught is the smallest and xn is the largest. Now, if you go on an analysis, you know, you're going to integrate over sets that are not intervals. Okay, so, you know, it gets kind of weird, but we are going to stick to intervals in this class here. But just know that there are ways to integrate functions over sets that are not integrals, or not sets that are not intervals. Okay, so here's an example. So let's say that I have this curve and I want to partition for where the curve starts and where it ends, where I'm interested in integrating. And so this is an example of a partition. Our starting point is a, x naught equals 0, and then I can have x1 as a half, x2 is right here, that's 4, and x3 is 6, and that's b. And notice that, you know, unlike what you're used to, the widths of these rectangles are different, and that's okay for our theory that we're going to develop here. Okay, so the height of the partition. So before, how did we look at height? We looked at height as the highest point on our curve over an interval, and that was either the rightmost point or the leftmost point when we looked at Riemann integration in Calc 1. But now we have some new language to describe this a little bit more accurately. So, given a partition x naught through xn, consider a subinterval. Okay, so we're just looking at an interval within a, b, and we're going to denote little mi as the infimum of f of x, so that x is in that subinterval, and we're going to denote capital Mi as the supremum, okay, of f of x, where x is in that subinterval. So you're looking at the lowest and highest values of x on a given interval. So let's go ahead and list these things out just based on our little picture right here, so we have a handle on them. So I have shaded in blue the infimums, the little mi's on each interval. So each interval, I have an interval here, I have an interval here, an interval here. So I have 3 intervals, and here notice that this is little mi. So I can just say that m1 is going to be equal to, and I'm just making up this number, this 3. This is 3. M2 is this guy, so that's the lowest point on this interval, and that's going to be 1, and I'm going to say M3 is the lowest point on this final interval, and I'm just going to say that that's 4. Okay, so then my supremums, so on this interval, the highest point is this guy. I'm going to say M1 is 4. Capital M2 is going to be this guy right here on this interval, so that's going to be at 4. And M3 is going to be this point. This is the highest on this interval right here, so that's 7. Okay, so those are going to be the heights of our rectangles. Okay, so now we have a definition. So recall upper and lower sums from calculus. Upper sums gave us an overestimate like we did with, where did we do it? Here. So we got an overestimate of the area under the curve here because we were looking at upper sums, and we had some extra area when we added up the areas of those rectangles. So same concept here. The upper sum is going to be the sum of the rectangles on a given partition. So if you have a partition from x0 to xn, you have n rectangles that you're working with. And if I want to find the sum of those areas, I just take the height of the rectangles and I multiply by the width. Okay, so I'm just taking this this partition and dividing it up into subintervals, multiplying. So the difference between these guys are going to be the widths of the rectangles, right? Like if maybe I'll just show you guys this picture here. So here's my picture. And the xi minus xi minus 1 is going to be this width right here. And the capital Mi is going to be the sup on that interval, so that's this guy. So I'm literally just multiplying base times height, okay? And then I add on the next subinterval. So the next subinterval I had this rectangle right here, and then I add on the next one. So I do x2 minus x1, okay? So that's this width times the height, and the height is going to be the highest point on this rectangle. So that's going to be this area. And then finally, for n equals 3, that's the last one here, I have x3 minus x2, that's going to be this width, times the height of the rectangle. Okay, so this is giving me my upper sum as the sum of these rectangles. And it is an overestimate because of the extra area up here that we're counting. So the lower sum is just what you think it is. Instead of looking at the supremum on an interval, on a subinterval, we're looking at the infimum. Okay, and so we're computing these rectangles that are completely contained in the curve, but it's a lower estimate, so we're actually underestimating, as you can see here. So again, we're looking at the difference between the xi's. So the x1 minus x0 is the width times, this time, the infimum. So what's the infimum on this interval? Well, it's going to be the lowest point right here, and so that's what we're calling the height of the rectangle. So we're going to take this area of the rectangle, we're going to add on to it next one, x2 minus x1 times infimum. x2 minus x1 is this, times the infimum is this guy. Okay, so we're looking at this rectangle. And then add on the third one, and you get your lower sum. Notice that this is an underestimate because we're not taking into account this area that is under the curve, right? Okay, so you've probably seen this idea before, but yeah, there it is, upper and lower sums. That's our definition. Okay, so now we're going to talk about refinements. Okay, so if we have a partition, x0 through xn, of an interval from a to b, a partition Q is a refinement of P if P is contained in Q. And so when we refine partitions, we're actually getting better and better estimates for the area under the curve. When we add more and more rectangles, the estimate gets better. That's the idea of refinement. So consider the following. So here we have some upper sums. So we have this function, f, in solid black, and we're giving an upper sum estimation with these 3 rectangles. And we have, so this is x0, x1, x2, and x3 is b. And if we look downstairs, we have a refined version. So we have all of the original points. We have x0 is here, We have x1 is here, x2 is here, and x3 is here. But notice that we're adding some more points in. We're adding this guy in. We're adding this guy in. We're adding this x in. We're adding this x in. And this one. So this partition is going to be the new green x's plus the original points. And so this guy is a subset of this guy, just like we have in our definition here. P is contained in Q. So this is the Q is the refined X points. So the green points along with the red points that we already had. So similarly with the lower sum, so we have these original points, x0, x1, x2, x3, and we have our refined points here. So this is x1, this was x2, x3, but now we're adding on some green points here, 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 and here, and here. Yeah, so this is the refined lower sum. And notice that the refinements are giving a better estimate of the actual area under the curve. So that's a key idea here. All right, and let's see. Are we going to prove this? I don't think we're going to prove it, but let's just talk about the intuition behind it. So if you have a function and a partition, if Q is a refinement, then the following happens. So the upper sum of the original partition is going to be greater than or equal to the upper sum of the refined partition. Okay, and the lower sum of the partition is going to be less than or equal to the lower sum of the refinement. So in other words, we're getting closer to the actual value with the refined partitions. Okay, so that's that. Here's another proposition that we're not going to prove, but we're just going to mention. If you have a partition, then the lower sum is always going to be less than or equal to the upper sum. Okay, that's, I think, fairly intuitive, right? The lower sum, it should be less than or equal to the upper sum. Now, if P1 and P2 are any partitions of AB, no matter how refined one is, you're still going to have the lower sum is going to be less than or equal to the upper sum. Okay, so that is refinements and lower and upper sums. So let's see what we have next on the agenda. Okay, so now that we have defined upper and lower sums, we can now define what the upper and lower integral of a function are. So let's say that we have a function and it's bounded. Okay, this is very important. Okay, so I'm gonna, highlight this. We can't integrate a function on an interval where the function is unbounded, right? Because if it's unbounded, it's either going off to positive infinity or negative infinity, and how are we going to compute the area? In more advanced classes, there are ways to do this, but for now, we're just going to say, no, a function, we cannot integrate if it's unbounded, okay? Okay, so first of all, our function's bounded, and let curly P be the collection of all partitions of this interval A, B. The upper integral of f is defined to be the infimum of all upper sums, okay, the smallest such upper sum. And the lower integral is defined to be the supremum of all such lower sums. Okay, so we're looking at all partitions and we're finding the absolute largest lower sum over all partitions. Okay, so let's see what's next on the agenda. Integrable. Okay, so here's our definition. So a bounded function, again, we need that hypothesis, bounded. If, maybe on your homework, hint, hint, wink, wink, if you're listening to this video, on your homework, if you have a function that's unbounded, it's automatically not integrable on that interval. We need boundedness to even consider a function being integrable. So a bounded function is integrable if the lower integral equals the upper integral, okay? And we say that the integral from a to b of f of x dx is equal to L to the lower integral equals to the upper integral. Okay, so let's do some examples of this. So claim constant functions are integrable, all right? So what is a constant function? Well, we know that constant functions are integrable. I mean, we know this from just our life experience. So let's say we have a constant function. This is f of x. Okay, so here's our function. Here's our x-axis. And let's say that this value is c. Okay? Okay, I don't know what's happening. I think people are drag racing down my street. It's fine. Everything's fine. So let's say that this thing is going from a to b. Okay, maybe that's where my function's defined, from a to b, this constant function. And let's write it out. So suppose we have this constant function from a to b to r, where f of x is equal to c for all x in my interval a to b. All right, and so we're trying to show that the lower integral equals the upper integral. Okay, so the lower integral is equal to the supremum over all such partitions of the lower sums. So for an arbitrary partition, so if P is a partition, we have that our lower sum, by definition, is just the sum from I equals 1 to n, depending on how many rectangles I'm using, mi, where this is the infimum on each subinterval, xi minus xi minus 1. Okay, so if we just expand this out, okay, if we just expand it out, we have, if starting at I equals 1, we have m1 times x1 minus x0 plus m2 times x2 minus x1, and so forth, right? We go up to mn times xn minus 1. Okay, and so keep in mind, this is the infimum on each subinterval. But guess what? This thing's constant. So the infimum and the supremum are going to be equal to c on any subinterval, right? There's no like going up or down. The infimum is just c, right? There's nothing that is smaller than c on any subinterval, okay? And so the point is that we can sub in all of these things with c, these infimums, and when I do that, I can pull out a c, right? These are all equal to c, and I can pull out a c, and now I have this telescoping sum where a bunch of stuff cancels. So this is going to be x1 minus x0 plus x2 minus x1 plus dot 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 plus xn minus xn minus 1. Okay, and so the telescoping part, so what does that mean? That means that I have a bunch of stuff that's canceling out. I have x1 minus x1 cancels. I have x2, a minus x2 is going to cancel. And all I'm going to have left at the end of the day is this minus x0 and this positive xn. So this is going to be equal to c times xn minus x0. Now remember, with a partition, your nth term is going to be b, and your x naught term is going to be a. So the start and the end of your partition. So this turns into c times b minus a. And so this was just the lower sum of an arbitrary partition. But guess what? Any partition is going to have this guy, right? Because like I was saying, the infimum is going to be the same along this constant function. There's no like going up or down. So your smallest value is always going to be c, right? And so the point is, like, when I take the supremum, so this is the lower integral, when I take the supremum over all such lower sums, over all such, and I'm just gonna leave out the rest of this, but the point is that you're gonna have the same thing for each partition. And so this is just gonna be c times b minus a. And we know that this is true just from Calc 1, right? Because if I'm integrating from a to b of c, let's say with respect to x, well, we know what this is. The antiderivative we just have, we're looking at c times x from a to b. And of course, this is just c times b minus c times a, which is c times b minus a. And that's exactly what we have here for the lower integral. Now, the upper integral, it's the same idea, right? And I'm not going to, work it out because it's the same idea, but the idea is that the upper integral is the infimum of the upper sums. And again, because this constant thing, we can carry out the same exact computation, but instead of little mi, we're looking at capital Mi. But the point is that since capital Mi is the sup over any such subinterval, the sup is still c. Like, there's nothing higher than c. So you're going to have the same exact computation, and you're going to get that the upper integral is also equal to c times b minus a. And since these guys are equal to each other, f is going to be integrable. Okay, so that's the idea here. Let's go ahead and look at another example of a function that's not integrable. So remember this function from when we looked at continuity. This is the Dirichlet function. Okay, so we have our domain is from 0 to 1, and we're defining our function to be 1 if x is rational and 0 if x is not rational. And we claim that this function is not integrable. And I think this is kind of cool. I don't know. I think this whole thing is kind of fun to to look at and to see, because I don't know, you think in a naive way like that this is integrable. Like, just intuitively you think, oh, well, this, I could make like boxes and just add up boxes, and that's going to be the area. I mean, it's such a seemingly simple function, you would think it'd be integrable, but it's not. So let's take a look at why this is. So remember this crazy thing. Okay. Now, it's not true. Like, we can integrate discontinuous functions. So that's not necessarily the problem here. But remember what we have. Okay, so this is our function f of x. And if x is, and we're looking from 0 to 1. Okay, so there's our interval here. And so let's say this is f of x equals 1. So if x is rational, it's going to equal 1. So there's a bunch of stuff that's rational between 0 and 1. And it's going to be 0 if x is irrational. So again, we have some dense subset here where x is irrational. And so why is this not integrable? Okay, so here's the reason. So every single subinterval, it's exactly what you think it is. It's just like with the continuity problem. So if we have a subinterval from 0 to 1, let's say xi minus 1 to xi. So I'm just saying any kind of subinterval, like maybe this guy. Okay, that's my xi to xi minus 1 to xi. So every subinterval of 0, 1 contains a rational and an irrational. Okay, and so this is just because of the density of the rationals and the irrationals in the reals. Any subinterval, no matter how small, is going to contain a rational and an irrational. And hence, in any of these subintervals, we have that our supremum on the subinterval is going to be 1, right? Because I'm going to have some rational right here, and so some rational on the some rational, and it's going to have a value of 1 on this subinterval. So that's going to be the supremum, and the infimum is going to be 0, right? There's going to be some irrational in this interval that that corresponds to an output of 0. Okay, so what does that tell us about the upper and lower sums? All right, well, if we consider an arbitrary partition and we look at of 0, 1, and we look at the lower sums, that's going to be equal to I equals 1 mi xi minus xi minus 1. Okay, and remember, in each subinterval, no matter how small I make it, this guy's going to be 0, right? That's going to be the infimum. So since that's 0, this whole sum is going to just be a sum of zeros, and so that's going to be 0, and hence the supremum over all such partitions is going to be 0. I mean, we're taking the supremum of a bunch of zeros, that's 0. However, if we look at the upper sum over an arbitrary partition, okay, we have partition from I equals 1 to n, capital Mi, which is my supremum over a subinterval. Well, we said over any such partition, my supremum is going to be 1. So this is going to become I equals 1 times xi minus xi minus 1. Okay, and we have some telescoping going on, right? If we expand this thing out, we're going to get x1 minus x naught plus x2 minus x1 plus ... all the way to xn minus 1. Okay, and so the telescoping, when we cancel out those terms, we're just going to be left with xn minus x naught, which is simply b minus a, right? This is the end point. This is my beginning point. Now, what's b and a? Well, a is 0. That's where that's the interval that I'm looking at integrating over. So a is 0 and b is 1. And so this is just going to be 1 minus 0 is 1. So again, I have a single number, and if I take, this time I'm taking the infimum over all such partitions. So the infimum of the upper sums. And so this is just going to be the infimum of 1, which is just 1. Okay, and so we have that this is equal to the upper integral. So the upper integral is 1, but the lower integral was 0. Now the upper and lower integral need to match. So since they do not, this function is not integrable. So since the lower sum, or the lower integral does not equal the upper integral, this means that f is not integrable. I can't spell. Okay. All right. So let's go ahead and recall a theorem that we did very early on in the course. This was the supremum analytic theorem. So there was another this was the sup version of the analytic theorem, and we also had the inf version. So just recall this, what does it mean to be a supremum of a set? So say we have a subset of the reals, then the supremum of that set A is equal to alpha if and only if the following two conditions are met. The first condition is that alpha is an upper bound of A. So remember that alpha has to be bigger than or equal to anything in A. So that's the upper bound. And then the second condition is given any positive epsilon, alpha take away epsilon is not an upper bound of A. Okay, so that means that there is some x in our set, so that x is actually bigger than our alpha minus epsilon. Okay, so let's take a look at this theorem. So let's say we have a function f from a to b, and it's bounded. Then f is integrable if and only if for each epsilon positive there exists some partition, p epsilon of a, b, where the upper sums minus the lower sums with that given partition is less than epsilon. Okay, so how do we think about this intuitively? Okay, so we know that f being integrable means that the upper integral equals the lower integral. And so that means that the lower sums are getting closer and closer to the upper sums. And so, we can think of this inequality here as, well, epsilon can be as small as it wants. And so we can think of the upper and these lower sums as getting closer and closer to each other. And hence we have the integrability criteria. So let's go ahead and prove this theorem. All right, so we'll start with the forward direction, which is the more involved direction, I think. And so what we're going to suppose is that f is integrable, and we're going to show that this implies this condition. Okay, so let's go ahead and start then with the forward direction. So suppose f is integrable, and let epsilon be bigger than 0. Remember, this is supposed to hold for all epsilon, so we just choose epsilon bigger than 0 and show that this inequality has to hold. Okay, so what does it mean that f is integrable? Well, going back to our definition, that just means that the upper integral is equal to lower integral. Okay, so we have the following. We have that uf equals, well, maybe I'll write it out actually. Since f is integrable, we have lower integral equals upper integral equals this guy. Okay, and so what do these two things mean? Just going to the definition of lower and upper integral, we have that the lower integral is equal to what? That's equal to the infimum. Oh, sorry, not the infimum, the supremum of the lower sums over all partitions. And the upper integral is going to equal the infimum of the upper sums over all partitions. Okay, and these two things equal this integral. Okay. So now we're going to appeal to the supremum and the analytic the supremum and the infimum analytic theorems. All right, so this guy equals a sup of a set. Okay, so this guy equals a sup of this set. And this guy also equals the inf of this set. So we can appeal to this theorem here. And we have an epsilon bigger than 0. And so we can say that there's something in our sets so that that something is bigger than the sup minus epsilon. Or in this case, we're going to do epsilon over 2 so that we get some nice cancellations. Okay, so by the supremum analytic theorem that we just reviewed, so I'm gonna call this set B just to be consistent with my notes, and this set A. So what does the supremum analytic theorem says? So it says that there's some element in B. So there is some. What do elements in B look like? They just look like this. L of Fp. So there's some L of Fp1 for which this guy, this is acting like our X, this L of Fp1. This guy is going to be bigger than the supremum, which is this guy. The supremum minus epsilon over 2, right? Any epsilon will work. Any positive number bigger than 0, so certainly epsilon over 2 will work. And so similarly, by appealing to the infimum analytic theorem, there is something in the other set. So there is some upper sum in this set. Let's call it U of Fp2. Okay, so there is some element in A. Say upper sum of Fp2 for which this holds. So U of Fp2 is going to be less than the infimum, okay? Which also, so this guy is the sup and the inf of the sets, of their respective sets. So this is going to be less than f of x, integral of f of x plus epsilon over 2. Okay? Alright, so the idea is like we want to combine these inequalities, so let's make sure that they are facing the same way. Let's see. Yeah. Okay, so in the first one, if I multiply both sides by a negative, again, in the first one I get negative L Fp1. It's going to flip the sign, and then everything on the right becomes negative. So this is going to become negative a to b f of x dx, and then this guy's going to become positive epsilon over 2. Okay, and so we can add these two inequalities together. And so what we're going to get is U Fp2 minus L Fp1 is going to be less than AB f of x dx minus AB f of x dx. Oh, I forgot my plus epsilon over 2 after that guy. But anyway, so the integrals are going to cancel, and then the epsilon over 2 plus epsilon over 2 is going to be equal to epsilon. All right, so this is going to be equal to, maybe I'll put equal epsilon there. And so what do we have? We have that U of Fp2 minus L Fp1 is going to be less than epsilon. Okay, but in our theorem, like we're almost there, right? But the issue is that we may have two different partitions here. But in our theorem, we only want one particular partition that's less than epsilon. Okay? So what are we going to do? Well, remember that we can refine our partition to make the approximation better. And so what we can do here is we can choose our partition to actually be the union of P1 and P2, and then everything works out. Okay, it's pretty neat. Okay, so what we're going to do is we're going to choose our partition, P sub epsilon, that we want in our theorem to equal the union of our two partitions, P1 and P2. Okay, and so then by proposition 8.1, we have the following. We have, so refinements actually refine, I think is what they say in the book. And so we have that the refinement, the lower sum of f of p sub epsilon, is actually going to be bigger than or equal to the lower sum of the original partition. So refinements give a better approximation of the sums, or the integral rather. And let's see. And here we have that this guy is greater than the integral of f of x minus epsilon over 2. This is going to be greater than this guy, f of x dx minus epsilon over 2. Okay, so again, this is by proposition 8.1 that this inequality holds true because this guy is a refinement of this guy. We're adding more points in there. Okay, and similarly, again, by the same proposition, we have that the upper sum of the refined version is going to be smaller than or equal to the upper sum of this guy. And by the above inequality, right here, we have that this guy is less than integral from a to b of f of x dx plus epsilon over 2. Okay, and this is going to imply that the upper sum of this p sub epsilon, again, just like doing the trick where we multiply both sides by -1, this becomes minus LFP sub epsilon, and this is going to be less than epsilon by just combining these inequalities right here, just like we did at this stage. Okay, so now we have what we want, and that direction is proven, right? We needed a single partition that would make this true. Okay, so let's do the other direction. So I'm gonna go ahead and erase some stuff because I'm out of room. So let me go ahead and erase some stuff. So we just did the forward direction. The backwards direction isn't as bad. It's not as involved. So let's just go ahead and erase. Okay, I think that will be good enough. Okay, so let's do the opposite direction. So now what are we assuming? Now we're assuming that for every epsilon, there's a partition where this inequality holds true. Okay, so let's go ahead and suppose that. So suppose epsilon is bigger than 0 and choose a partition p sub epsilon so that inequality holds true. And now we're trying to show that f is integrable. So we're trying to show that the upper integral equals the lower integral. Okay? So that u f p sub epsilon minus L f p sub epsilon is less than epsilon. Okay? And so, the idea here is, we're trying to show that f is integrable. And to show that it's integrable, we need to show that LF equals UF. The upper integral equals the lower integral. So we have to somehow bring that into the picture here. Well, we have upper sums and lower sums, given to us here in our problem. And we know some things about the lower and upper integral. So we know that the lower integral is going to be the supremum. Okay, by definition, it's the supremum of all the lower sums, which means that it's going to be bigger than or equal to, in particular, this lower sum. I'm just going to put in parentheses, soup. This guy's the soup of the lower sums. And similarly, we have that since the upper integral is the infimum of all the upper sums, this is going to be less than or equal to, in particular, this upper sum, u f p sub epsilon. And this is just, in parentheses, infimum. Okay, and so when I combine these inequalities, if I multiply both sides by a -1 up there and I add these guys together, what this is going to give me is that u of f minus L of f is going to be less than or equal to u f p e minus L f p e. We know from hypothesis that this guy is less than epsilon. Okay, and so now we have exactly what we want to have, because epsilon can be arbitrarily small. It can be, it can get as close to 0 as we want. So saying this, we'll say letting epsilon go to 0 from the right yields that this guy is less than 0 or equal to 0. If you want to think about it like that, so they're equal to each other, since this guy can get arbitrarily close to 0. So we have that the upper integral equals the lower integral, and therefore f is integrable, and we're done. So that direction wasn't so bad. Okay, let's do one more theorem. Okay, so as I mentioned before, we don't have to have continuity to ensure integrability. Like, we can integrate discontinuous functions because, we're just thinking about areas under curves, really. And, like, you can think of, like, something like this that's clearly discontinuous, but, like, you're like, oh, wait a minute, I can integrate that. I mean, that's not a big deal. I just look at the area under the curve. Not a problem. But anyway, this theorem is telling us that if it is continuous, it's guaranteed to be integrable. Unlike differentiability. Remember, we had something like that was continuous but not differentiable? Well, this theorem says continuity implies integrability always. Okay, so that's how, that's the difference between this and differentiability. Okay, so let's go ahead and prove it. We only have one direction to prove, just the forward direction. So we're going to suppose that f is continuous. So suppose f is continuous on AB. Well, AB is a compact interval. It's a closed and bounded interval. And so we can appeal to the extreme value theorem to say that f has to be bounded. Okay, right? We need boundedness to conclude, or to even say that something could be integrable. So since f is continuous on a closed and bounded interval by the extreme value theorem, it follows that f is bounded on AB. So how are we going to attack this? We're trying to show integrability, and instead of showing that the upper integral equals the lower integral, we're going to use this, we're going to appeal to this theorem that we just proved. And what we're actually going to show is that there does exist a partition for every epsilon where this inequality holds true. Okay? So that's what we're going to do. That's our plan of attack here. All right, and so another nice thing about being continuous on a compact set is that this implies uniform continuity. I can't remember what theorem that was. I should have looked it up, but it's in the section where we looked at uniform continuity. Okay, so let's write that down. Also, since f is continuous on a compact set, closed and bounded, AB, it is uniformly continuous on this set. That's nice. Uniform continuity is really, really nice. So what does it mean to be uniformly continuous? Then there exists some positive delta such that when the difference between x and y in this interval a to b is less than delta, this is going to imply that the difference of f of x minus f of y is going to be less than epsilon for every epsilon. For the sake of the proof, like to make things work out, we're going to choose our positive epsilon to be epsilon over b minus a. And this is completely valid because epsilon's positive, b minus a is going to be positive, right? Because it's, b is the greater number than a, and we're dealing with a closed interval here. So that's going to be positive, so there's no problem in choosing this as our quote-unquote epsilon. Okay, so this is what uniform continuity means. Okay, and remember, the difference between uniform continuity and regular continuity is that a single delta will work here for all x and y in our set AB. Okay, so what we're going to do is we're going to choose little n in the naturals so that b minus a over n is going to be less than delta. And it's going to become clear why we're doing this, but the point is that we can make n large enough so that this whole thing is smaller than any positive number, right? We can just make this arbitrarily close to 0, as close as we want. Okay, so we have this, and it's going to become clear why we need that in just a bit. And we're going to let a partition, so we're going to let p sub epsilon equal x naught, x1, all the way to xn, where x sub I is equal to how we defined it on the second slide, or the first slide. It's going to be a plus I times b minus a over n. Okay, so this is our partition here. So let's maybe draw it out. So here's a, this is x naught, here's x1, which is a plus b minus a over n, all the way to b equals x sub n. Okay, so now we know, we know that f is continuous on a to b, hence it's continuous on each subinterval of a to b. Okay, so let's write that down. Since f is continuous on AB, it's continuous on each subinterval. On each subinterval. So again, remember what the extreme value theorem said. It said that on an interval where f is continuous, it's going to achieve its supremum and its infimum. Okay, so by extreme value theorem, f achieves its sup and its inf on each subinterval. So that just means that there's some x in the subinterval so that f of x is equal to the inf and maybe f of x prime is equal to the sup. Okay? On subintervals. Maybe I should say each subinterval. That's better, I think. All right, so maybe we'll call f of x min equal to mi. So this is the infimum on each subinterval. This is the infimum. And we'll say that f of x max is going to be the supremum on each subinterval. So this is the supremum. All right. Well, then we have the following. We have x min, distance between x min and x max, is going to be less than delta because of this condition right here, right? So if we're looking at the distance between two x values in a subinterval, and since this guy is less than delta, then certainly x min minus x max will be less than delta as well. Okay, so we have that, and by uniform continuity, that's going to imply that f of x min minus f of x max is going to be less than epsilon over b minus a. Okay, and so this is going to imply, because what's f of x min? That's mi. What's f of x max? That's capital Mi. So we have that when we take that out of the absolute value, it becomes capital Mi minus little mi is going to be less than epsilon over b minus a. Okay, and so if we go back to our upper and our lower sums of our partition, then we have the following. So we have u of f p epsilon minus L of f p epsilon, just by definition, is equal to n I equals 1 mi xi minus 1 minus, okay, I'm just filling in what the definition says these things are. This is going to be little mi to xi minus 1. And then I can, since I'm adding to n in each of these pieces, I can simply factor out the mi minus the capital Mi minus little mi and combine these sums into 1. So this is going to become I equals 1 capital Mi minus little mi times xi minus 1. Okay, well, we just said that this guy was less than epsilon over b minus a. So that is going to imply that this whole thing if I just replace the epsilon over b minus a here, it's going to be less than I from 1 to n of epsilon over b minus a is xi minus 1. And this epsilon over b minus a is going to be constant because I chose an epsilon and the b and the a are fixed. They're the endpoints of the interval. So if I factor out that epsilon over b minus a, I'm left with this. And this is a telescoping sum. Right? There's going to be a bunch of cancellations. And so what this is going to end up being, and now it's not going to let me go further down the page, but maybe I'll just put an arrow right here to say that we're continuing there. Since this sum telescopes, what we're going to be left with is xn minus x naught. So this becomes epsilon over b minus a times xn minus x naught. And we know that this is b and this is a, right? So this is b minus a, and so that just equals epsilon. Okay, so we have shown that this guy is less than epsilon, and by theorem 8.1, that implies that f is integrable. Okay? So therefore, by theorem 8.1, it follows that f is integrable. All right. Well, that is our video, and thank you for watching, and I'll see you guys next time.